is a projectiles question from this particular CCEA Applied Maths A2 Pass paper. I think this one's from April 2021. So let's take a wee look then. It's question 2. John is taking part in the school science experiment. He has to create a rocket that can be projected at an angle of 60 degrees to the horizontal and fly across a pond as shown in figure 1 below. A and B are in the same horizontal level. The rocket is projected from A and must land at B. Show that the time of flight t seconds is such that this t equals root 3 u over g, where u ms to minus 1 is the initial speed of the rocket. So in this scenario, obviously for any sort of projectiles question, we're going to look at vertical motion and we're going to look at horizontal motion. So if we look at vertical motion here, we should be able to get what we have. I'm going to take upwards to be positive, and then u, v, a, s and t. So my u, let's take a wee look. I'm projecting that then vertically, so I'm not going across that 60, so that then is going to be u sine 60. We're not worrying about our v at the minute. Our a is going to be minus 9.8, or if I want minus g, there's a g there in the answer, so we're just going to leave that then, it's g. S, so what are we looking at? We're looking at the vertical motion. We effectively want to know the time of flight, so it's the time it's going up and back down again. So whenever it goes up and back down again, we're looking for the time whenever the displacement is 0, as in it's landed back where it started. So we have that, and then they've given a capital T to that, so we're going to substitute that in there using the formula S equals ut plus a half at squared. We're going to have 0 equals, so u sine of 60. Now hopefully I'm in degrees, I think I am here, that's okay, is root 3 over 2. So it's going to be u times root 3 over 2 times t. So how am I writing that? u t times root 3 over 2 minus g over 2, so that's the half, and the g, remember it's a minus because it's a minus g there, and then that's t squared. This then tidies up very slightly. I'm going to times through them by 2 just to get this tidied a little bit. So ut root 3 minus g t squared. This looks quite complicated here. It's a quite straightforward quadratic, however we look at it. So if we kind of factorize that and take out a common t, we would get 0 is t upon u root 3 minus gt. Sorry, you can just about see that, apologies there. We have that. So that means either t is 0 or u root 3 minus gt is 0, and rearranging this to get the t on its own, we get u, sorry, that's a u rather than a mu, u root 3 over g. Part 2. Hence, find the speed at which John should project his rocket to be successful in the experiment. So we know our time from the previous one. So let's see what we're going to do. We're now going to look at our horizontal motion. So how's that going to work out? It tells us our distance is then going to be 12.6 meters. And then our u of x, as in our horizontal motion. Let's go back to this. So I'm resolving this direction here, so it's u cos 60. And then my distance, sometimes we have s then for that, so distance is speed times time. So in this case we have 12.6, sorry I've changed my d for an s, I hope that's okay. U cos 60, cos 60 is nice and straightforward for us, it's just a half, so that's going to be u over 2 multiplied, and then the t that we had was u root 3 over g. So let's see if we can tidy this up. We're going to have then 12.6 is equal to root 3 u squared all over 2g. Do you see what I've done there? I've kind of multiplied this then by this. So I'm going to times this by 2g, and then I'm going to divide by root 3, and then I'm going to find the square root. So I'm timing 12.6 times 2 times 9.8 gives me that, and then divide by root 3, which is 142.58. U then is the square root of that, and that's going to be then 11.9. Find the speed at which John should project the rocket, so 11.9, then we get us across there. Final wee question: assuming u remains the same, suggest a change that would be made to maximise the horizontal distance covered by the rocket. Well, you can see that it's projected at 60 degrees, and so if we change that to 45, then that's obviously going to maximise the rocket. So change to launch at 45 degrees would work for us there.